Thank you to Dr. Nicolas Gisin of the University of Geneva on his musings concerning quantum correlations, also known as spooky action at a distance, and which we used to call quantum coupling. I believe we're considering the Einstein-Podolsky-Rosen response to the Copenhagen interpretation to quantum mechanics as postulated by Niels Bohr. Quantum mechanics' real foundation and birth as a valid theory begins with the derivation of Schrödinger's equation involving a Greek letter psi by Dr. Edwin Schrödinger. Both Edwin and Albert Einstein insisted that psi has nothing to do with probability, contrary to Bohr's postulate. Although stories are interesting, without the proper vocabulary, no story can make any sense. The vocabulary of Mother Nature, of the universe, is mathematics. Without knowing her vocabulary, you cannot understand a word she is saying. Hence the failure to understand the spooky nature of reality and recognition of the true genius of Schrödinger and Einstein. The word attraction evokes warm fuzzies. The attraction between the moon and the ocean doesn't explain why there are really two tides going on at the same time. There's a high tide when the moon is overhead, and there's also an equally high tide 12 hours later when the moon is on the other side of the Earth. We use mathematical modeling to explain this phenomenon. There are no physical laws to predict results. We can only predict results using mathematics. We try to describe a phenomenon using a mathematical model. We then try to solve the resulting mathematical problem and then try to transform the solution back into a physical reality. If we are incredibly lucky, unbelievably lucky, over the moon lucky, so lucky it's time to buy a lottery ticket, the mathematical solution matches physical observation and experiment. Yay! If we are unlucky in this endeavor, then Mother Nature has a good laugh at our expense, and we continue to constantly and doggedly chase after her, often in vain, to acquire her treasures. Far more often than not, we end in frustration. However, when she affords us a slight victory, the rewards are literally life-changing for us all. So, if you find yourself frustrated, then you're using the wrong mathematics. Let us look at tides, and let us look at this Nerf ball. If we pull on one side of the Nerf ball, the ball does not resemble the tides of the Earth's oceans. However, if we squeeze the ball, like wrapping it in a tensor bandage, both ends push outwardly, and we see this resembles the behavior of the tides. How come? It is because gravity is not a vector field. It is a tensor field. Both the Nerf ball and a four-dimensional Minkowski space qualify to be modeled by the biharmonic equation, and as a result, we are successful in describing both a Nerf ball and the tides using this mathematical model. This is important here. Because we have a physical object, such as a Nerf ball, which obeys the same mathematical principles involved in modeling oceanic tides, we can use it to demonstrate and to increase understanding. This is known as using a physical model. The Nerf ball is a physical model of oceanic tides. It's also a pretty good model of a four-dimensional Minkowski space. However, we have been warned by Dr. Schrödinger that no physical model exists to demonstrate behaviors in the world of the quantum. Although there are some attempts at physically modeling the atom and nucleus, they are very restrictive and soon break down if placed under any stress. If we are to really comprehend the world of the very small, as described by Schrödinger's equation, then we should listen to the admonitions and warnings of its author. The only comprehensive model of quantum mechanics is a mathematical model, and this mathematical model has nothing whatsoever to do with tossing dice. There are three sets of differential equations which describe physical phenomena. There are Maxwell's equations for electricity and magnetism, the Einstein field equations which combine gravity and electromagnetism, and Schrödinger's equation, which describes the world of the very small. The Einstein field equations have boundary conditions which are both time and space oriented, and Schrödinger's equation also has boundary conditions in space and time. Remarkably, the boundary conditions for both the Einstein field equations and Schrödinger's equations are the same. We learned that in high school. Outside of the boundary conditions of Schrödinger's equation, we are in an L2 space known as a Minkowski space. Although we use a fourth-ordered norm to account for the off-diagonals in the stress-energy tensor, mostly we can utilize the properties of an L2 space to describe events. That is, stuff happens, and happens at a maximum velocity, which happens to be the speed of light. It's a Banach space. As every engineer knows, if we change the differential equation describing events, we change the entire space. Schrödinger's equation is simply the diffusion equation with a linear term added onto it. And there is no way a Banach space can be defined through solutions to the diffusion equation. So, if we are within the boundary conditions of Schrödinger's equation, all bets are off as far as predictability, causality, determinism, or even probability are concerned. This is Alice down the rabbit hole and through the looking glass, looking for Bob. All understanding having any relation to classical physics has no place here. To state it even more bluntly, time and space, in terms of a measure using clocks and rulers, are totally out. They have no bearing. There is no cause to an event in Wonderland. There is just an event. That's all there is. And the event occurs entirely throughout the space contained by the boundary conditions, simultaneously. Stuff just happens. This is completely within the realm of reality. It is just a property of the diffusion equation. So, let us say Alice meets Bob in Wonderland. That is, within the boundary conditions of Schrödinger's equation. And because they are in Wonderland, they are indistinguishable. Because of this, let us say that they have become entangled. While they are in this space, we cannot tell them apart. So what happens to Alice happens to Bob and vice versa. However, if we wish to take a peek at what Alice and Bob are doing, we need to send in Charlie. Somehow, to detect anything in quantum space, we have to call on Charlie. And if Charlie becomes entangled with Alice, which he has to do to try to figure out what she's doing, Alice forgets all about Bob, and Bob forgets all about Alice. Alice and Bob are no longer entangled and move on. To demonstrate how we know this, if there is a quantum party of many simultaneous entangled events, meaning the events all occur within the boundary conditions of Schrödinger's equation, results of the party are seen spontaneously spread out on a detector as a wave phenomenon, showing that stuff happens spontaneously across space. However, if Charlie crashes the party, the detector shows a particle phenomenon. The party is over. This is, of course, the double slit phenomenon. All that is happening is that should the boundary conditions of Schrödinger's equation not be violated, then the rules of Wonderland pertain. Should these boundary conditions be violated, then the rules of Minkowski pertain. The explanation to understanding spooky action at a distance also resolves the double slit experiment. Without Charlie, you cannot see what is going on. And Charlie is a buzzkill.